Hi everyone, good morning. In this section we're going to look at spherical mirrors. So spherical mirrors are mirrors with a curved surface that is a spherical surface. So it's as if it could have been cut from a larger sphere. And this is what I've drawn here. So if you imagine this sphere, we could cut out a piece of the surface in two ways, either cutting out this side and then maybe making this outer surface shiny and polished so that it's a mirror. Or we could cut out this side and then make the inner surface shiny. And then we have two different types of curved mirrors, which I'll get to in a second. So with this concept of these mirrors coming from a larger sphere, we can define two important quantities. So the radius of curvature, which is a length, meters, or often we use centimeters for this section as long as all the distances are in the same unit. So the radius of curvature is the radius of the mirror as if it was cut from a larger sphere. And radius of curvature is used in other areas of physics, not just for mirrors. And that's essentially what it means. If this curved surface were to complete a sphere, what would the radius be? Okay, and then there's C, the center of curvature, which is the point where the center of the sphere would be located. So it's at a distance of r from that center of the mirror. So what I mean is that if we were to draw the mirror on an axis here, usually there's an axis that's drawn through the midpoint of the mirror here and perpendicular to the surface of the mirror. And this axis is called either the principal axis or the optic axis. Then on that axis, the point that is a distance r from this midpoint of the mirror is called C, and this is the center of curvature. So you can picture it as this sphere completing all the way around and then get an idea where C would be. If you're doing a sketch, sometimes that helps. Okay, so there are two types of spherical mirrors. The first one is concave or converging. In this type of mirror, it's defined by the fact that parallel rays would reflect and then appear to converge at a single point on the principal axis. So I've drawn it here, the parallel rays hit the mirror and then reflect and they meet at a point. Now this also, if we were to cut this shape from the sphere, we can imagine that the inside surface is polished so that we have this concave surface. Okay, the second type is a convex or a diverging mirror. In this case, parallel rays reflect from the surface of the mirror and then they diverge from the mirror. So they spread apart instead of converging at a point. However, if you extend the reflected rays like we did for the plane mirror, the extrapolated reflected rays converge at a point on the principal axis. And this is as if we were to cut a surface of the mirror, cut a piece of the spherical shape as I did before, and then make the outside the mirror, so shine this outside so that it's reflective. For either type of mirror, a very important quantity is called the focal length. So the focal length is the point where the parallel rays, so rays that are directed at the mirror parallel to the principal axis, converge or diverge from both after reflection on the principal axis. And so this is a point, but also the same symbol F is used to mean the focal length. And in that case, it's the distance from that midpoint of the surface of the mirror to the focal point on the principal axis. And a relationship exists between this focal point and the radius of curvature. It's half the radius of curvature. So we have F equals R over 2 for spherical mirrors. Now we're going to look at how to use a few special rays in order to locate the image formed by a spherical mirror. So we know that rays are directed in all directions from an object, but we can choose a few of them that help us easily locate the image. And this is a very systematic approach, so let's look at how to do that. Okay, let's look at image formation by a concave mirror. So we know that light rays from the object go in all directions. We can use a few of these light rays called special rays that will help us to locate the image. I'm going to go through 4 different special rays. So first of all, when you're drawing a ray diagram, you should start with your principal axis, that's here, or the optic axis, and then draw a vertical line to represent the mirror. We really want a vertical line to direct all of our rays there since we can't accurately draw the curvature of the mirror. But then on the line you can draw in the mirror that shows the correct shape so someone looking at your diagram knows if it's concave or convex, which we'll get to in the next section. Okay, then I've just drawn an example here So we would label the focal point and then the center of curvature and label the object. So the object could be located anywhere. For right now, we'll look at the object between C and F. So I'm going to label it with an O to represent the object and then an arrow. And this will just be a sketch. We'll look at doing a scale diagram in the example. Okay, so the first ray we'll do is the parallel ray. It travels parallel to the principal axis and then reflects through the focal point. So using my ruler, I'm going to show you how to draw this. Okay, so I'm just going to use my ruler, direct it at the mirror, and if it's a sketch, I'm just going to make this as parallel as I can. Actually, in general, we'll just estimate what parallel is, and then reflect this through the focal point. So I'm lining up my ruler to that point and drawing the ray in here through the focal point. Okay, and that's the parallel ray. Now moving up, our next option here is the focal ray. So the focal ray is going to travel through the focal point and then reflect parallel to the principal axis. So it's almost inverted from the last ray. So I'm going to take the top of the arrow through the focal point until it hits this line that I've drawn for the mirror and then reflect parallel to the principal axis. So something like that. Oh, that didn't work. Okay. Fix that. There. Okay, so the ray hits the mirror and then it reflects. And we would draw all of these on the same diagram. I'm just drawing them here so you can see them individually. Okay, so two more. Now let's look at my third option here, the center of curvature ray. I made up the names, by the way, just so we can keep track of them. So this ray is going to travel through the center of curvature and then reflect back along the same path. So this one can be a little bit trickier to draw depending on the object placement. Sometimes it doesn't quite fit on the diagram. Let's try it here. So I'm going to extend the mirror line. This is just a tool to allow us to find the image. So you can always extend this line. It doesn't depend on the actual height of the mirror. It's just giving us a way to locate where the image is. So I want to connect the top of my object arrow to this center line C and then to the mirror to make a straight line like this. And then I'll draw that straight line because it's incident. I'll just show you. Okay, there we go. What happens is the ray leaves from the top of the object arrow, theoretically, travels to the mirror and then reflects along the same line. So it's back here. Okay, and then our last ray here, number 4, is the law of reflection ray. All of these rays follow the law of reflection. It's not always easy to see if it's not a flat mirror. For this one, we can see it fairly easily because it's going to hit the midpoint of the mirror. So this one is directed at the midpoint of the mirror, then reflects according to the law of reflection. So it's going to go from the top of the arrow to this midpoint along the principal axis. And then I'm just going to estimate for now the law of reflection here. So I want it to reflect along the same angle as it was incident, so something like that. So that these angles are equal. And I think it helps to use this as your last ray because then you have an idea of where it's going, and if it's a sketch, you still don't necessarily need to measure. Okay, so I've just made one more diagram so I can show you how we would do this to find an image. This is just rough, a rough sketch here, so we could draw it to scale if we needed to, otherwise it gives a good kind of rough estimate of where the location of the image is. So how to find an image, we're going to choose 3 rays. Choose 3 of the 4 that I've just introduced. The first 2 will locate the image and the third is a check, and you can choose whichever ones you like. I'll usually start with the parallel ray. So I'll draw the parallel ray here. Parallel hits the mirror and then it's going to reflect through the focal point. Okay, and then I don't know if this is long enough, but I can extend it later. Then I'm going to go through the focal point. So now I'm drawing the focal ray. I'll just grab another color. Okay, so the focal ray is going from the top of the arrow to the mirror line, and then it's going to reflect parallel to the principal axis. Okay. So our image point is where these reflected rays cross. This would be a real image based on the placement of this object. So it forms an image where real light rays cross in front of the mirror, which is a real image. Now we're going to do one more ray just to confirm, and you can choose. So I'm going to do the law of reflection ray. So I'm going to take the top of the arrow to this midpoint of the mirror, and then reflect that. And now I have an idea, okay, it should go there, and it looks like it does, so it works really well as a check. All right, and we have 3 rays. You can do a 4th if you want. I won't draw the 4th in, but I'll just show you with my ruler. It would go like this, through the center, the top of the arrow, and it would still roughly intersect there. Maybe I need to turn mine a little bit more, like that. Okay. So here is our image, and now I'm going to draw the image in from the principal axis to the point where these light rays cross, and label it I. And then we can get an idea of the characteristics of the image based on what the ray diagram looks like. So this image would be real. It's inverted, we can tell because it's below the principal axis. And maybe it's not as obvious, but it's magnified as well. Okay, I've written out some rough guidelines here for ray tracing. So first we're going to draw the scenario. So draw your principal axis and then set a scale if needed. Often we just need a sketch, but if you are doing a scale diagram, make sure you have that. You can use a different scale on the horizontal axis from the vertical axis, just like you would with a graph, so make sure you just clearly label that. And then, okay, draw the mirror shape. So please do draw whether it's concave or convex, and then draw a mirror line so that we have a nice vertical line to direct our rays to. Also label the focal point and label the center of curvature on your principal axis. Okay, then we'll draw in the object. So draw a straight upward arrow to represent the object, and we can label that O. And from the top of the arrow, the point of the object, we're going to draw 3 special rays. I went over 4, so choose 3. You have your option of 3. 2 rays locate the image, and then the 3rd will confirm it. So we want to draw any 3 of those 4. And then once you've drawn them, make sure you extend them until they converge. And so I'll show you how to do this after if it is a virtual image. If it's a real image, we just extend the rays until they cross. And then where they cross, this is the image, and we're going to draw an arrow from the principal axis down to the image point, a straight line, and that's our image point. You can label it I. And then if needed, we can measure DI, HI, or we can calculate them, and we can state the characteristics of the image. Images are classified by 3 general characteristics. Either the image is real or virtual. I have gone over in the previous section on plane mirrors what a virtual image is. A real image occurs if real light rays cross at the image point. In this case, for a real image, if you were to hold a screen up at the image point, you would see an image on the screen. And a spherical mirror can produce a real image that would form in front of the mirror. And we do get real images for concave mirrors. Okay, then if the image is upright or inverted, and you can see this by drawing a ray diagram, we'll also calculate, and I'll show you how to find that through the calculation. Then we want to say if the image is magnified, reduced, or the same size as the object. And again, we can get a rough idea whether it fits one of those 3 based on looking at the diagram, but we can calculate exactly what the magnification is, and I'll introduce those equations now. We can also use an equation to calculate the image distance or object distance or focal length because of the relationship between these 3 quantities. And this is the equation here. It's called the mirror equation. We have 1 over f equals 1 over do plus 1 over di. So f is the focal length, do is the object distance, di is the image distance. And each of these distances are measured from the mirror, And usually they're in units of meters or centimeters. So we can use any length units as long as we use the same for all quantities. Okay, then we have the magnification equation, which is HI over HO. So this is image height over object height. And there's one more way to write this magnification equation. It's negative DI over DO. We do want this negative here in this version of the magnification equation, but not in this one. And I'll explain the signs just below. So the sign convention for this mirror equation is focal length is positive for a concave mirror. So right now we'll use positive. It's negative for a convex mirror. Then DO is positive in front of a mirror. So DO is almost always positive. We call the front of the mirror where the object is. And then DI, the image distance, is positive if the image is real, which for a mirror means that it's forming in front of the mirror. DI is negative when the image forms behind the mirror, and this is virtual, and we'll look at this case as well. Okay, and then magnification, a magnification of greater than 1, the absolute value, means the image is magnified. If the magnification is less than 1, it's reduced. And then there's a sign as well, and a positive sign for magnification means it's an upright image. It's the same orientation as the object. And a negative sign for the magnification means that it's inverted. Example 3, a 10 centimeter high object is 60 centimeters from a concave mirror. The mirror's focal length is 40 centimeters. Use ray tracing to find the position of the image and determine its height. Use the mirror and magnification equations to verify your results from A. Okay, if you like, you can use this same scale that I'm using. This is on the back of the end of the Module 5 lecture problems if you want to print that. Otherwise, you can just set the same scale here. So you could use 1 centimeter equals 10 centimeters along this principal axis. These boxes are just over 1 centimeter, but that scale should still work on your paper. And then we want to mark the focal point at 40 centimeters. The object, O, is at 60 centimeters and C is at 80 since it's twice F. And we will need a vertical scale, so I've chosen the same actually, so one side of the box, or you could do 1 centimeter equals 10 centimeters. And you don't have to draw in all these grid lines if you're drawing this yourself. You can just make note of the scale on the bottom somewhere, so maybe the top, you could put 1 centimeter equals 10 centimeters. And then we have our scale for the horizontal. This is the same scale as the vertical as well. Okay, so now the next thing, you should draw in your mirror line because this image is not exact, the radius of curvature of this mirror. So we'll put in a vertical line here where we can direct our rays. And then, all right, let's start with 3 rays. You can choose any 3 of the 4. I usually, again, start with this parallel ray. So I'm going to use this line here to go parallel with the mirror line and then reflect through the focal point here. Okay. It's the parallel ray, and then I'll use another color and do the focal ray. So here through the focal point and then to the mirror line. And then I'm going to reflect here. Okay, mine's not quite long enough, so I'm going to have to extend a little bit. Trying my best to make that parallel. And then now I can see I need to extend this line a bit until they cross. There we go. Okay. So we see our image point, but let's do one more ray to check since 3 is required. So we're going to go, I'm going to do the law of reflection ray. So just looking, my center ray would work as well. We could do it like that. It would just go a little bit almost off the page here, so that's why I'm going to choose this law of reflection ray. So top of the arrow to the midpoint of the mirror. Yeah, which is there, okay. All right, and then I'll direct it here following the law of reflection. Okay, and then I can see my image point, which is almost right at the end here. and that's I. Okay, even when we're doing this to scale, we may not get the exact image distance because we are estimating the law of reflection, we're estimating parallel lines, but it does give us a very good approximate location. So we're seeing the image at about 120 centimeters, and it's clearly magnified. We can see the image height looks like it's about 20 centimeters. But let's check this now with our mirror equation. All right, so I've written this out here, and we can just solve for di. 1 over di is 1 over f minus 1 over do. And I'll just flip that. You could rearrange and get a common denominator if you want to. So 1 over f minus 1 over do. And then this is 1 over 40 minus 1 over 60, which does give me 120 centimeters as expected from my diagram. Okay, then the magnification is negative di over do. So negative 120 over 60, which gives us negative 2. And this negative sign tells us that it should be inverted, which it was, and it should be magnified by a factor of 2. So then we also know the magnification is hi over ho, or we could write hi equals m ho, so negative 2 times 10, which gives negative 20. Again, that negative means that it's below the below the principal axis, or also means that it's inverted compared to the original. Example 2, a converging mirror has a radius of curvature of 40 centimeters. An object 10 centimeters high is placed 15 centimeters from the mirror. Locate the image, describe its characteristics, and draw a ray diagram. Okay, so let's calculate first, and then we'll do the diagram. We're given R, HO, and DO. So just make sure you do check the sign. This is a concave mirror, so we have positive, but if they're giving you the radius or even the focal length in the question, usually it would be positive, but we may need to put it as a negative if it's convex to use in the formula. Okay, so let's calculate DI. Again, 1 over F equals 1 over DO plus 1 over DI. So we get DI equals 1 over F minus 1 over DO. So DI is 1 over 20. This is our radius of curvature, and we have F is R over 2. So 1 over 20 minus 1 over 15. And this gives negative 60 centimeters. So remember what this negative means. It's going to be behind the mirror, and it's going to be virtual. And this will happen anytime we move the object inside the focal length. So from this equation, we can see that actually that's when we get negative, when we have a DO that is less than the focal length. So that's giving us this negative here. So I'll show you how to draw the diagram for a virtual image in a second. The magnification then we have is negative DI over DO. So negative of negative 60 over 15 is 4. So we know that the image will be virtual, upright, and magnified. Okay, let's look at how to do the ray diagram for a virtual image. So again, I'm using this 10 centimeter scale per box on the vertical side, and then I have the focal length at 20 and the object at 15 centimeters from this mirror, and I've drawn in this vertical mirror line to help the diagram again. Okay, so I'm going to start with the parallel ray. So I'm going to use that grid line here and go parallel, hit the mirror line, and then reflect through the focal point, like this. Okay, parallel ray, and then now I'll do the focal ray. So this one's a little bit different because the object is within the focal point. So I'm still following the same rules. I'm going to, I might need this line a little bit longer. Okay, so I'm going to connect the focal point and the top of the arrow like that. There, I'm trying to do it carefully. And the mirror line, and then draw that ray in. And then it's reflecting parallel, so try to line this up as parallel as I can. And it reflects here. So I don't need to draw this portion. Really, the ray starts at the top of the arrow, and then it will connect to the mirror line and reflect. And notice that these two rays, already we can see that they diverge. They're not going to meet at a point. So again, this ray actually starts here. There. Okay, so what we can do is extend them back behind the mirror like we did for the plane mirror in order to find the image. So I'm going to line that up and extend. And then the same thing for the reflected portion. Make sure you're extending the reflected rays. So that's going to extend here. Okay, and that's our image, and it does look quite accurate, like it's at about 60 centimeters here. So we'll do one more ray. There's no room to do the center of curvature ray, so I'm going to do the law of reflection ray again. There are some cases where that center ray is really useful, but and then I find it helps to line this one up so you know where it's going. Since it's just a check anyway, we already have found the image. Something like that. And then we'll draw it in, dotted lines behind the mirror, since these aren't real rays. And that's the reflected ray here. Okay, and now we have all three meeting at a point, so we can draw in the image around here. Mine actually looks a little bit past 60, but it is fairly close, and that's about what we can expect when we are doing some estimating, even in a scale diagram. Okay, and we can clearly see that it's upright, it's virtual since it's behind the mirror, and it's magnified, and it does look like it's about 4 times magnified, so that could be 40 centimeters there for the final image height. We've seen now that the characteristics of an image formed from a concave mirror depend on the placement of the object in relation to the mirror. So let's take this far case where we have the object placed outside C. In that case, we get an image that's real, inverted, and reduced. Then if we move it closer, we put it at C at the center of curvature. In that case, the image is real, inverted, and the same size. Now if the object's between C and F, our image will be real, inverted, and magnified. And then if we move it to the focal length at point F, this is a bit of a turning point between real and virtual images. Right at F, the image is formed at infinity. Doesn't mean we can't see it. Our eye can focus on objects that are essentially at infinity or very far away. It takes parallel rays and focuses them to form an image. Okay, and then within that point F, so closer to the mirror, at an object distance less than the focal length, we have an image that's virtual, upright, and magnified. On the other hand, a convex mirror always forms an image that is virtual, reduced, and upright. So let's look now at the special rays for convex mirrors. Let's now look at ray tracing with convex mirrors. Convex mirrors always form a virtual image no matter where the object is placed. When you draw a convex mirror, again draw your principal axis. Because the front of the mirror looks like this, if we were to complete a sphere, it would be on this side, actually behind the mirror. So the focal point and the center of curvature for a convex mirror are behind the mirror. Or if we put the object on the left side like we've been doing, they're on the right side. Okay, so again the same for special rays, they just look a bit different now that we have a new setup. So the parallel ray travels parallel to the principal axis and then diverges from the focal point. So what we're going to do is take our ruler and make sure that it's parallel, our best parallel approximation here, and draw that line. And then turn the ruler so that it connects with that point of connection on the mirror to the focal point. And the ray diverges from that point, like this. So it reflects on the left side of the mirror, and it appears as if it's coming from this focal point. Okay, let's keep going. Then we have the focal ray. So the focal ray is going to travel towards the focal point and then reflect parallel to the axis. So top of our object arrow to the focal point. And I'm going to stop at the mirror. It's traveling that way. And then it's going to reflect parallel. So now I line my ruler up parallel to the principal axis and reflect parallel. Like that. All right, and back to number 3. Okay, so the law of reflection rate, this one and number 4 are essentially the same as for a concave mirror. So it's directed at the midpoint and follows the law of reflection. Again, all of the rays do. This one's just easy to see. So here. And then reflecting, I would always draw this one last as well as a check. And then our center of curvature ray, which goes to the center. So I'm going to connect the top of the arrow and this C point here. So this looks interesting because I'm going to draw it connecting to the mirror and stop, and then it reflects along the same line. So it's like this actually. And I'm going to extend these rays behind the mirror because now we see that they are all diverging. So I'll show you how to do that when I draw them all together. Okay, so now we'll locate the image. I'm going to start with the parallel ray. So going parallel to begin. And then it's going to diverge from the focal point. So this time when I'm locating an image, now that I know the rays diverge, we want to always extend the reflected ray. So that's here. I'm going to extend it behind the mirror and a dotted line. Okay, and then the next ray was the focal ray, so connecting the top of the arrow to the focal point. Hits the mirror and then it reflects parallel. And again, we're going to extend that parallel portion behind the mirror, extending the reflected ray. And we see our image point, but let's do the 2 other rays too. Okay, so now we have the law of reflection ray, so top of the arrow to the center of the mirror here. And then reflecting, and I want to aim it at that point, kind of cheating, but it's just a check. Okay. And then I'm going to extend that reflected portion as well. It all works out. And lastly, I don't have another color. I'll do black again. This one's going to go from the top of the arrow to point C, and look at that. This ray is really useful here. It lines up nicely. So again, a straight line and then a dotted line behind the mirror to extend the reflected ray, which this time is along that same line towards the center. And now all of these rays form an image here. That's our image. So it is virtual because real light rays don't cross at this point. It's behind the mirror. So the 3 characteristics are virtual, upright, and, oh, I want to write reduced. What's the last thing I'm writing? There we go, reduced. That's an R. Okay. So virtual, upright, and reduced. And actually, wherever the object is placed, these 3 characteristics are always the same for a single convex mirror. Example 5, a convex mirror has a radius of curvature of 30 centimeters. An object of height 20 centimeters is placed 40 centimeters from the mirror. Where is the image? Draw a ray diagram to verify your result. Okay, so we have R and F. Make sure F is negative. R is a radius, so it's not really wrong to just write 30, but we do need at least that negative sign on F. And then DO is 40 and HO 20. And we want the image distance, so let's rearrange for DI. I've already done that here. 1 over DI is 1 over F minus 1 over DO. So DI equals 1 over negative 15. centimeters minus 1 over 40. And that gives negative 11 centimeters. And again, that negative sign tells us that it is virtual, so it's forming behind the mirror. And didn't ask for the height, but let's find that as well. So magnification, negative di over do, is negative 11 over 40. So positive 0.275, which gives hi of 20 times 0.275, so 5.5 centimeters. And now we can verify with the diagram. Okay, so looking at this last diagram here, I've chosen 2 boxes, so 1 box is 10, and then 2 is 20 centimeters on the vertical scale, and our object's at 40 centimeters, and then the focal point is at 15 centimeters, remembering to put that behind the mirror. Okay, now 3 special rays, starting with, let's start with the parallel ray. Okay, I'm going to go off the grid here with my rays, but that's not an issue. So here, hitting the mirror line that I've drawn in, and then that's going to reflect as if it came from the focal point. So I'm turning my ruler, and while I'm here, I'll extend this with a dotted line behind the mirror, since I know that these rays are going to diverge. There. Okay, that's the parallel ray. And then I'll draw in the focal ray, so top of the arrow directed towards the focal point. Just adjusting that a bit. Okay. Hits the mirror and then reflects parallel. Dotted line behind the mirror. Solid line in front. And we need 1 more ray. There's not enough room for C on this side, just in my diagram, so I'll do the law of reflection. So towards the center. And it does look like that's going to line up quite nicely. Okay, and this is our image here. I would say that is pretty close to 11 centimeters, which is what we were going for. So it worked out pretty well, and we wanted a height of 5.5 centimeters, which if this is 10, that does look like it could be 5.5.